Let's begin. We're trying to plot polar curves now. Polar curves are particularly difficult because we're used to thinking in terms of rectangular coordinates, but there are a couple of techniques we can use. Now, the first way of drawing the polar curve is, of course, by using a tabular notation. You can plot theta against r, and the more values of theta you sample, and the more values of r you have, like you can start by 0, 30, 60. You can have more of these values, and then you can make a better curve. That would be a simple approach, but we want a more qualitative approach that gets us there quicker. So I'll use sort of a graph. Now first I need to plot this in sort of a rectangular styled uh, coordinate system. So essentially I'm plotting something like this. Okay. Now for these sort of functions, it's very easy to plot them. It's not that difficult. I'll show you how to do that. The first thing you need to do is, of course, plot the dependent part. Sin x function, if this is 90, 180, 270 and 360 respectively, sin x is basically this. This is the typical sine curve. Then you have to do it 4 times. This is a simple scaling argument. You scale it 4 times, so it becomes something like this. And then you do a -4, which means this curve, this 4 sin x curve, should get inverted. And then you have -3, which means it has to be shifted. So you have to pick this curve up. Basically I didn't draw the whole curve in one go, so I should draw it in one go, and maybe I can better represent how it should be shifted. So you can shift it -3 downwards. So this is now what you're looking at. Now this is important. This curve would be pretty important in plotting, and we'll get to that in a moment. But because I've done it a little haphazardly, I'll show it through this graph. This is the same curve. We're going to look at the first cycle, which means from this point to somewhere over here. Okay, when it again becomes -3. Okay, so this is one full rotation. You can see it's exactly the same. We have this point, and we have this point, and then this point. Okay, so let's start. So as we're understanding x as theta and y-axis as radius, it's easier to see from here now. You can see. Okay, so let's start. The first thing is at 0 degrees, which is this direction, you have -3. So the radius would be in the opposite way, so it should be here. Then at 90 degrees it's -7. So 90-degree ray is this. It's -7, so it should be below 1, 2, 3, 4, 5, 6, and 7. So it should be somewhere over here. You've made the first 2 points, but the important question is how to join them. Now, of course, you see the absolute value of the radius is increasing as you're going from 0 to pi by 2. So what you should do is you should rather arbitrarily approach it to 7 or -7 as you're going through the first quadrant. Of course, your angle is increasing in the first quadrant, but your radius, as it is negative, the curve would be traced in the third quadrant. Now, symmetry demands from pi by 2 up till this point somewhere over here, I think, where you get a -3 again exactly. I cannot pinpoint it per se, but you know that there would be the 0 point over here as well, which would be at pi. Okay, so at pi it should be, or 180 degree, it should again be -3. So at pi, which is this angle, it is going to be -3, so it will be plotted in the opposite direction over here. Again, because of symmetry, you can see this section and this section of the curve are symmetric, so the radius would follow a similar trend and approach -3. Now after this point there is some sort of confusion how to plot the curve. Now after this, you can see that there is a point where there would be 0 as the radius. So you will approach 0 radius. As this curve is given in radians, so it's almost 4 radians. At 4 radian angle, you can see the radius is becoming 0. So 4 radians is somewhere in this in the second quadrant, because pi radians is 180 and pi is almost 3.14. So 4 should be something more than that, almost like 230. So let's suppose it's almost 230 degrees. Now what we need to do is we need to carefully think of a 230 degree line like this. This is a 230 degree line. Now because the curve has to enter the 0 radius, has to come to the 0 radius at an angle of 230 degrees. So what we need to do is we need to make it something like this, so that it drops and it coincides with this 230 degree line. So we have to be sure of that. Okay. So we've done the 230 part, and I'll try erasing the excess now. Okay. So the idea was that it's going to enter the r equals 0 at an angle of 230. So that is why we're using a 230 degree reference here. Okay. So after this, after it enters almost at this 230, meaning that this angle is 230. After it enters at 230, we made the curve till here. At 270, we know the curve has to go to 1. So what is 270? 270 is the ray below, and 1 in that direction is a positive number. So we expect it to be here. And we see as the angle increases from this 230, the radius is going to increase in that direction. So this should be the curve. Now we've made the entirety of the curve, and we don't need to worry about anything because the curve is now done. Because you see there's a symmetry around the 3 pi by 2 point for the graph. So it should be the same exact graph for the last quadrant. So that is how you make a polar curve, and it slightly resembles what a limachon should look like, although it's a little sketchy. Of course, this is one technique you can use. You can resort to other techniques as well, in which you use a tabular form. But I like using the graphical form for one very important reason, is that it tells you where the function is increasing or decreasing, so you sort of understand the general shape of the function easier. Acha. Now for the second question, you see it's a rather atypical form of polar equation. You usually see a linear polar equation in R. You don't see a quadratic sort of component. Actually, you cannot plot this on Desmos. I've checked. You cannot plot it on Desmos. They don't plot quadratic equations in polar. So you might need a different graphing calculator to plot this, but this is a very well-known common plot. I'll tell you before starting, it's something like this. Okay. So this is a fairly simple plot, but we would go in a slightly different way this time. We'll use more of a tabular form for this question. So first of all, I'll like to simplify this. So the r should equal under root cosine of 2 theta. Now you should remember that this implies, that necessitates, even looking at this, you can say that cos 2 theta needs to be greater than 0 or positive, because if cos 2 theta was negative, there would be a negative number under the under root, and that would be problem. So we need cos 2 theta to be positive. When is cos 2 theta positive? So that's the question. So in which quadrants is cos theta positive? First of all, let's see where cos theta is positive. Here, and then in this coordinate. In this quadrant, it's positive. Okay. These are the two quadrants where cos theta is positive. Where is cos 2 theta positive? Let's see. So as the angle is doubled, so the first 45 degrees would become the first 90 degrees. So the first 45 degrees would give you a positive values. Values from 45 till 90 would give you a negative value, because that is the case. Now at 90, the double of 90 is 180. Okay, and from 180 through 270, it should also again be negative. 270 divided by 2, that is 1, that is 3, 5, 135. So at a certain angle of 135, okay, so at an angle of 135, till 180, you'll again have a positive value, because 135 times 2 is 270, and 180 times 2 is 360. So this corresponds to the fourth quadrant. So in a sense, if we're assessing the domain of theta here, okay, so theta should go from 0 to 45, and then 135 to 180. Okay, now theta can go a little more, so you can have 180, because theta keeps on going, so there's no restraint on theta or 2 theta. So if you have theta from 180 till, what is 360 plus 90? That is 360 plus 90 is 450. So the half of 450 is 225. So from 180 to 225, you should again have a positive value for cos theta. And likewise, you'll have something over here. There would be a skipping of 90 degrees, but after that, from you can guess 45 below 360 is 315. So from 315 to 360, there would be a positive value. So we just need to target these areas, and we'll be able to do the plot. Okay, so here are the reference values we need to plot. So we plot from 0 to 45, then 45 to 135 we skip. Why we skip? Because it's not part of the domain. So let's start by plotting from 0 to 45. So at 0 degrees it's 1. So we'll have to actually make a different arrangement. Let's erase all of them, and let's assume this is r equals 1. Okay, because it would be a little more clear, because our maximum r is 1 in this case. So r equals 1 is here, and then at 15 degrees, which is a very small angle over here, it would be 0.93, so it would be decreasing like this. And then at 30 degrees it would be 0.07, but at 45 degrees it would be 0. So at 45 degrees, which is dead in the middle of the first quadrant, so it should come inside to this inside towards the r equals 0 point at an angle of 45. Okay, so this would have a slant of 45. Okay, so this is the first part. Okay, and after this you have 135. Now you skip over the angles in between, because they're not part of the domain by definition. So what you need is 135. So 135 is something here. It's like the 45 for this second quadrant. So it's something over here. So it's 0 over here, and it grows to 180 till 1. So at 180 it's 1. At a slightly lesser it's like this. So you see that this would be something like this. Okay, so that is that. Okay, so that is part of the curve. Of course, I've told you that it needs to be something like this. Where do we get the rest of this then? Okay, so you see, we can do two things now. We can plot for the rest of the domain. I've told you that from 180 to 225 there would be another acceptable domain. So if you see, you can relate these points the same sort of radii. So you can similarly plot from 180 to 225, which is like the middle of this quadrant. 225 is like that, so it could plot something like this. Okay, and likewise, I won't go into the detail for the last one, which is 315. It would be a similar sort of curve. You can, of course, the domain theta keeps on going. Theta can increase arbitrarily large. Now theta would repeat this after a 360 cycle. After a complete 360 cycle, the shape would be repeated. Or you can do another thing. You can get tricky and you can put a plus minus over here. And if you had put a plus minus over here, you would have plotted both the possible values of r. That could be argued as well, but in that case you would have just needed to use this much, because this first part would have been replicated by a part over here, and the second part would have been replicated by a part over here, and the shape would have been completed. So these are the two ways we keep doing this.